In this video, I will be talking about ionization energy. So, what is ionization energy? The definition is as follows. The first ionization energy is the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions with N+ charge. Do remember this definition, as this is sometimes tested in the A levels. To explain this, it just means that the ionization energy is the amount of energy required to remove the outermost electron from its atom or ion. Let me use copper as an example. The electronic configuration of copper is as follows. The first ionization energy of copper is 745 kilojoules. This is the first ionization energy of copper. This means that to remove the 4s1 electron, which is the outermost electron, it will require 745 kilojoules of energy. Now, the second ionization energy of copper is 1958 kilojoules. So for the second ionization energy, we are going to remove an electron from the Cu+ ion to form Cu2+. The electronic configuration of Cu+ is as follows. Hence, to remove the outermost electron, a 3d10 electron, it will require 1958 kilojoules of energy. Notice that for the same element, ionization energy will always increase as we move from the first ionization energy to the second ionization energy to the third ionization energy, and so on. This is because we need more energy to remove an electron from a more positively charged ion. Hence, this gives it a higher ionization energy. Going back to the above example, this means that we will need more energy to remove a negatively charged electron from the Cu+ cation, which is positively charged, as compared to the amount of energy required to remove an electron from the Cu atom, which is neutral. Moving on, what are the factors that affect ionization energy? We need to know that first ionization energy decreases down a group and increases across a period. Why is this so? Firstly, we need to understand that the ionization energy is determined by the effective nuclear charge. The effective nuclear charge is defined by the net nuclear charge experienced by an outer electron. Hence, if an outer electron experiences a weaker effective nuclear charge, it will be easier to remove an electron. If it experiences a stronger effective nuclear charge, it will be harder to remove an electron. So, in order to calculate the effective nuclear charge, we will take the nuclear charge minus the shielding effect. The nuclear charge is basically the attraction for the outermost electrons by the nucleus. As the number of protons in the nucleus increases, the nuclear charge increases. The shielding effect, on the other hand, reduces the strength of the nuclear charge. This is caused by the presence of inner shell electrons, which reduces the electrostatic attraction between the outermost electrons and the nucleus. So, as the number of principal quantum shells increase, the shielding effect increases. There can also be shielding effect by electrons in the same quantum shell. Electrons in the S subshell can shield electrons from the P subshell. However, do note that this is very small as compared to the shielding effect of the electrons in the inner principal quantum shells. So now, we can finally explain why first ionization energy decreases down a group and increases across the period. As we move down the group, the number of quantum shells increase. Because of this, the outermost electron is further away from the nucleus. Electrostatic forces of attraction between the nucleus and the outermost electrons are weaker. Less energy will be required to remove the electrons. This results in a lower ionization energy. As we move across a period, the number of protons in the nucleus increase. This increases the nuclear charge. Because we are still in the same principal quantum shell as we move along the period, the shielding effect remains relatively constant. Since nuclear charge increases but shielding effect remains relatively constant, the effective nuclear charge will increase. Hence, there will be stronger electrostatic forces of attraction between the nucleus and outermost electrons. Because of this, more energy will be required to remove the outermost electrons, which results in a higher ionization energy. So, do remember all these keywords that I have mentioned above, and do include them in your answer when asked about ionization energy trends. As previously mentioned, first ionization energy generally increases across a period. However, do note that there are two anomalies to this trend. If we look at this graph of first ionization energies across period 3, we can observe that in general, the first ionization energy increases from sodium to argon. However, do you notice that there is a small dip between magnesium and aluminium, and another small dip between phosphorus and sulfur? Magnesium is a group 2 element, and aluminium is a group 3 element. Phosphorus is a group 5 element, and sulfur is a group 6 element. This is very important to note. This is because there will always be a small dip between group 2 and group 3 elements, and group 5 and group 6 elements as we go across a period. So, what causes the dip between the group 2 and group 3 elements? Why does aluminium have a lower ionization energy than magnesium? Let us write out their electronic configurations. Realize that aluminium has an additional 1 3p electron as compared to magnesium. The 3p subshell is further away from the nucleus as compared to the 3s subshell. Hence, there is a weaker electrostatic force of attraction between the nucleus and the outermost electron for aluminium as compared to magnesium. Hence, lesser energy will be required to remove the 3p electron from aluminium, resulting in a lower first ionization energy for aluminium. Next, why is there also a dip between the group 5 and group 6 elements? What causes sulfur to have a lower ionization energy than phosphorus? Again, let us write down their electronic configurations. Do you realize that phosphorus has a half-filled 3p subshell, while sulfur has a partially filled 3p subshell? We can visualize this better by drawing the electron-in-box diagram. Realize that the 3p electrons in phosphorus are unpaired, while in sulfur, 2 of the p electrons are paired. Hence, as the paired electrons in the 3p subshell will experience inter-electronic repulsion, less energy will be required to remove one of the 3p electrons. Thus, it will have a lower first ionization energy. Do remember and familiarize yourself with the explanation for both of the dips. This dip can be observed across all periods, and this is something that is commonly tested. Now, here is the graph of the first ionization energies in period 2. Notice that again, there is a dip between the group 2 and group 3 elements, and between the group 5 and group 6 elements. Try explaining this on your own, using a similar explanation to the one above. Now, the last thing that we need to learn would be how to interpret successive ionization energy data. In the A-level syllabus, you will be required to read successive ionization energy graphs. To explain this, let me use an example. So, let us look at this graph. We have to find out what electronic configuration this graph represents, and hence determine the identity of the atom. For a successive ionization energy graph, the y-axis represents ionization energy, while the x-axis represents the number of electrons removed, or the ionization energy number. When we remove the first electron, it is known as the first ionization energy. When we remove the second electron, it is known as the second ionization energy. This is why we can use both terms interchangeably for the x-axis. So, to begin, as we can see, there is a large increase from the first to second ionization energy. This large increase implies that the third electron is in an inner quantum shell. Hence, we can deduce that this is a group 1 element. The second to 9 ionization energy seems to show a gradual increase. After that, there is another large increase from the 9 to the 10th ionization energy. Again, this implies that the 10th electron is in an inner quantum shell. Therefore, it is likely that all these 8 electrons that are removed are from the second quantum shell. It can't be from the third quantum shell because the third quantum shell also has 3d electrons. Thus, we can deduce that the first 6 electrons are 2p electrons, and the next 2 will be 2s electrons. Note that there is a very slight increase from the 8 to 9 ionization energy, since more energy will be required to remove the 2s electrons, which are closer to the nucleus, as compared to the 2p electrons. This might not always be very clearly drawn on successive ionization energy diagrams. Now, with this information, we can finally deduce that the first electron is the 3s electron, and the final 2 electrons are the 1s electrons. Hence, with all this information, we can tell that the electronic configuration of the atom shown in the graph above is 1s2, 2s2, 2p6, 3s1. This gives us sodium. Do note that questions on successive ionization energies can ask you to determine the group of the element or the electronic configuration of the atom. For these questions, you need to explain clearly how you get to your final deduction. In other cases, they might even ask you to draw out successive ionization energies on a graph. For this, remember to clearly show both the small and large increase. So, in this video, we talked about ionization energy, we explained the factors that influence ionization energy, and lastly, we touched upon successive ionization energy diagrams. If you found this video helpful, please support the channel with a like and subscribe. Also, we have finally reached the end of our 4-part series for A-level atomic bonding.